Welcome to the deep dive. Today, we're tackling really one of the biggest questions in AI, true reasoning. We all know large language models, LLMs, are incredibly powerful, but how they actually think. That's been a bit of a mystery. And we're looking at whether the answer is always building bigger, training harder, or maybe it's about unlocking something already inside. We've got this fascinating new paper from IBM Research and ETH Zurich called Eliciting Reasoning in Language Models with Cognitive Tools. So our mission for you today is to unpack this approach because it kind of challenges how we think AI learns to reason at all.
It really does. It taps right into this ongoing debate. Is the kind of advanced reasoning we see in top models something taught, maybe through reinforcement learning, or is it actually, an inherent capability, just lying dormant, waiting to be elicited? We saw all that speculation around models like OpenAI's O1 preview, right? And the open source community jumping in with things like DeepSeek R1. This paper, though, it offers a different angle entirely.
Right, so let's dive into that core question. Taught or unleashed? When models like O1 preview first appeared, they were suddenly much better at coding, math, reasoning.
Yeah, huge leaps.
And the immediate thought was, okay, it must be techniques like chain of thought, getting them to show their work, and reinforcement learning, RL. That seemed to be the key.
Absolutely. The release notes even confirmed RL was crucial. The model learns from feedback, rewards.
Digital carrot stick. Yeah.
Exactly. But how it worked, the specifics, that was still pretty unclear. Lots of theories floating around, maybe super detailed reward labels, maybe some kind of self-correction mechanism. Then DeepSeek showed up, and they demonstrated that you could get really high-quality reasoning with essentially a combination of supervised fine-tuning, first like giving it a good base lesson, and then RL optimization.
Okay, so RL was definitely part of the mix, but maybe not the whole story, or at least the how was fuzzy. But then things got even more interesting, right? Just when people thought they had a handle on it.
Right, exactly. The plot thickens, as they say. Researchers started digging a bit deeper. People like Yu et al., just this past year.
And what do they find?
Well, they looked at the base models. Think Qwen 2.5 base, DeepSeek V3 base, before all the intensive RL fine-tuning. And surprisingly, these base models were already showing strong reasoning, even exhibiting these aha moment self-reflection patterns.
Whoa, okay, so the kind of stuff people thought only came after RL tuning.
Precisely, which led you to propose something really interesting. Maybe RL isn't actually teaching new reasoning skills from scratch.
Okay, so what is it doing then?
Their idea is that RL might mainly just be biasing the model's output, basically pushing it to generate the kinds of high-reward answers it already knows how to produce deep down. It's more about uncovering or surfacing existing abilities than installing new ones.
Huh. So RL is an elicitation mechanism, not necessarily an infusion mechanism.
You got it. And that immediately begs the question, if RL is one way to elicit these latent abilities, what other ways might there be?
Which brings us neatly back to this paper, because they looked somewhere completely different for inspiration, didn't they? Not just more AI techniques, but cognitive psychology.
Exactly. They drew inspiration from cognitive science, looking back at work like Anderson et al. From the late 90s. The idea there was that human reasoning isn't one big monolithic process.
Right. It's more like a set of specialized tools.
Kind of, yeah. Structured, modular cognitive operations that we orchestrate. Like our brain has this toolkit of thinking functions.
Okay, and how did that idea translate into AI? Was there a stepping stone?
There was a technique called cognitive prompting, developed by Kramer and Bowman last year. It was basically prompt engineering, structuring the LLM's prompt into stages.
Stages like clarify the goal, break down the problem, combine the results, something like that.
Pretty much, yeah. Goal clarification, decomposition, integration. And it did show real improvements in things like arithmetic and common sense reasoning. It guided the LLM through a more structured, sort of human-like thought process.
Okay, cognitive prompting sets the stage. But this new paper adds a twist. You mentioned modularity.
Yes, that's the key innovation here. Cognitive prompting was still kind of one big sequential prompt. This new work takes those cognitive operations like understand the goal or break down the problem and makes them discrete, self-contained tools.
Like actual tools the AI can call within an agentic framework.
Exactly. But here's the really neat part. Traditional agentic tools usually call external things a calculator, a web search, a code interpreter.
Right.
These cognitive tools are different. They encapsulate reasoning operations within the LLM itself.
Whoa, hold on. So the LLM is calling itself, or like a specialized part of itself?
Sort of. Think of it like the LLM invoking an internal thought module. Each tool has its own prompt template. It runs in a kind of sandboxed context, focused on just that one cognitive task, like understanding the question deeply or examining its own answer for flaws. And then the structured output of that tool gets fed back into the main reasoning process. The crucial thing is the LLM decides which tool to use and when. It's not forced into a rigid sequence like cognitive prompting.
That sounds much more flexible, like giving it a workshop full of specialized thinking tools it can pick and choose from.
That's a great analogy. And the theoretical benefits are pretty clear. It should reduce interference between different types of thinking. It potentially allows for compositional generalization, combining basic thinking skills in new ways for new problems.
Like a chef using basic techniques to invent a new recipe.
Exactly. Much more flexible than just following a fixed recipe every time.
Okay, this is fascinating. Let's get specific then. What are these cognitive tools? You mentioned 4 of them.
Right. They defined and implemented 4 key ones in this research. First up is understand question.
Okay, sounds fundamental.
It is. Inspired by human goal management, it prompts the LLM to really break down the problem, pull out the core concepts, the relevant info, maybe even flag theorems or methods that might be useful. It's all about setting up the problem clearly right at the start.
Makes sense. What's next?
Second is recall related. This taps into analogical reasoning. The tool basically provides the LLM with relevant, already solved examples of similar problems.
Ah, like giving it a hint based on past successes, guiding it towards a known solution path.
Precisely, helping it see the pattern. Third is examine answer.
The self-reflection tool.
You got it. This is where the LLM checks its own work, its current reasoning trace. It looks for flaws, wrong assumptions, calculation errors, things it might have missed.
It's internal quality control.
Exactly. It helps it pause, reconsider, maybe correct its course before giving a final answer.
Okay, that sounds incredibly useful. And the 4th one?
Backtracking. This one comes into play when the LLM hits a dead end or realizes it's gone down the wrong path and got an incorrect intermediate result.
So it helps it rewind.
Yeah, pretty much. It helps the LLM revert back to a previous step that was correct, summarize where things went wrong, and then explore a different, hopefully more promising line of reasoning. It's like consciously deciding to backtrack and try a different approach.
Okay, understand, recall, examine, backtrack. A nice little toolkit for thinking. And how does the LLM know when to use them?
That's handled by what they call the cognitive tools prompt. It's a FISTM prompt, sort of like setting instructions for the AI. It encourages the LLM to call these tools, almost like calling Python functions, whenever doing so would make the task clearer or the solution more robust.
So it's not forced, but encouraged. The LLM still has agency.
Yes, that's the idea. It allows the LLM to dynamically decide the best strategy for tackling the problem, using the tools it deems necessary.
All right, so the theory sounds compelling. Modularity, flexibility, internal reasoning tools. But does it actually work? How do they test this?
They put it through its paces, focusing on math benchmarks, things like AIME 2024, Math 500, AMC problems.
Why math specifically?
Because math is heavily reliant on clear, step-by-step reasoning. It's a domain where you can pretty unambiguously tell if the reasoning process led to the right answer. It makes it a great testbed for this kind of capability.
Good point. What models did they try it on?
A range. Open-weight ones like Quen 2.5, Llama 3.1, Llama 3.3, and also powerful closed models like GPT 4.1 and even O1 Preview.
And how did they measure success? Just getting the right answer?
Primarily using pass-at-one accuracy, so getting the correct final answer on the first attempt. For problems where the answer isn't just a number, they actually used GPT 4.1 as a judge to verify if the reasoning and the result were correct.
Okay, the setup sounds solid. What were the results? Any aha moments there?
Oh, definitely. First off, even giving the LLM just one of these tools often provided a significant boost over the polyline model with no tools.
Really? Just one tool made a difference?
Yeah. For example, Llama 3.370B Instruct, just using the backtracking tool alone, saw its score jump by over 26% on one benchmark.
Wow. Okay. That shows the power of even focused interventions. What about the modularity aspect? Did that prove better than the older cognitive prompting?
It did, consistently. When they compared this modular cognitive tools approach against the more monolith, step-by-step cognitive prompting, the tools approach came out ahead.
How much better?
The gains varied, but on Llama 3.370B, the modular tools boosted performance anywhere from about 4% to over 27% above the baseline, clearly beating the monolithic prompting. It really validated the idea that giving the AI flexible access to these reasoning modules is more effective.
So modularity wins. And what happened when the LLMs had the full toolkit available? All 4 tools?
That's where you saw really robust improvements across the board, especially on the tough math problems. Take Quen 2.532b Instruct on the AE 2024 benchmark. Its baseline accuracy was about 17%. With the cognitive tools, it jumped to over 32%.
That's almost double, just by giving it these internal thinking tools.
Pretty much, yeah, just by enabling it to use these structured reasoning processes.
Hmm.
But here's maybe the most eye-opening result. They wanted to see how close this approach could get to models specifically fine-tuned for reasoning using RL, like O1 Preview. So they took GPT 4.1, a very capable model, but not specifically RL-tuned in the same way as O1 for reasoning.
Right.
And they simply gave it the cognitive tools. No extra training, just the tools. Its pass at one score on AIME 2024 went from about 26.7% up to 43.3%.
43%. Just from adding the tools, how does that compare to O1 Preview?
O1 Preview scored 44.6% on that same benchmark. So just by adding these untrained cognitive tools, GPT 4.1 got incredibly close to the performance of a model heavily optimized for reasoning via RL.
Okay, that is compelling. It really strengthens that argument that maybe a lot of the capability is latent and these tools are just helping the model access it more effectively.
Exactly. It suggests that structured modular workflows might be a powerful way to unlock inherent reasoning, potentially without needing massive RL fine-tuning efforts.
Can we make this even more concrete? Maybe walk through an example from the paper. You mentioned a GCD problem.
Yeah, the greatest common divisor problem. They gave Llama 3.18b, instruct the task of finding the GCD of three numbers, 33329, 2961, and 1491.
Okay. And the baseline model? Without tools.
The baseline model got it wrong. It came up with an answer of 3.
All right. Now, what happened when it had the cognitive tools?
It approached it very differently. First, it intelligently decided to use the understand question tool.
To make sure it knew what GCD meant and what the goal was.
Exactly. Broke it down, identified the core task. Then, recognizing it needed a precise calculation, it chose to use the use code tool.
Ah, so it generated Python code to actually compute the GCD.
Correct. It wrote the code to handle finding the GCD of multiple numbers. And then importantly, used the examine answer tool.
To double check its work.
Right. It looked at the code it generated, the output it got, and verified the logic. Only after that self-check did it provide the final answer.
And the answer was?
The correct answer. The one.
Nice. So you can really see the difference. The baseline sort of guesses, while the tool-equipped version has this methodical, verifiable process. It understands, plans, executes, and checks.
Precisely. It shows the guided modular reasoning in action. The LLM is actively directing its own thought process using these specialized internal skills.
So stepping back, what are the broader implications here? This seems like more than just a neat trick for math problems.
I think so too. It really suggests that a significant chunk of LLM reasoning ability might come from these latent capabilities baked in during pre-training, and these structured modular workflows are an effective way to bring them out. It could offer a path towards more interpretable AI reasoning, maybe more efficient too, compared to just relying on massive reinforcement learning pipelines. It could be an alternative or maybe a powerful complement.
And the real-world impact. I can see how having more transparent reasoning would be huge.
Definitely. Think about high-stakes areas, healthcare, maybe finance, legal analysis. Understanding how an AI reached a conclusion is critical for trust and accountability. If the AI uses understandable cognitive tools, its process becomes less of a black box.
It could also make advanced reasoning more accessible, right? If you don't need a giant RL setup.
Potentially, yes.
Wow.
It might democratize access to these higher reasoning capabilities if they can be elicited through clever prompting and tool use rather than just massive compute for RL training.
Of course, it's still early days. What are the limitations they acknowledged?
Well, the tools themselves were still designed by humans, manually crafted. They're not automatically discovered yet.
Okay.
And the main testing ground was math. While that's great for evaluating reasoning, the specific prompts for these tools might need adjustment to work well in other domains, or even with different families of LLMs.
Makes sense. Needs more generalization testing. What about the future? Where does this research point?
Lots of exciting directions. Could we automate the discovery of new cognitive tools? Could we integrate this tool use framework with reinforcement learning? Maybe RL learns how best to use the tools.
Ah, interesting.
And of course, applying this whole concept to much broader areas beyond math, scientific reasoning, planning, maybe even creative problem solving.
So, wrapping this up, what's the big takeaway? It feels like we've uncovered a potentially different path towards more capable AI.
I think the core message is that unlocking greater intelligence in LLMs might not always be about more data or bigger models. It might be about structure. about guiding their internal processes in ways that perhaps mirror effective human cognitive strategies.
Giving them better ways to think, not just more facts to know.
Yeah, exactly. It encourages us to think about guiding the intelligence that's already there, rather than assuming we always have to build it from scratch with complex training regimes.
And for you, listening to this, it really poses a fascinating question. If breaking down thinking into these modular cognitive tools works so well for AI, what does that tell us about our own intelligence? What other human skills could be modularized and maybe embedded in AI? How could this fundamentally shift how we build and maybe how we interact with truly intelligent machines down the road? Something to ponder. Keep exploring, keep questioning. Until next time on The Deep Dive.